Hello, Mr. Luong. This is Morellatrin in AP Physics C Period 1. This is my take-home FRQ number 2. It's video part 1 covering letters A through C. Letter A is asking us to explain why angular momentum is conserved and give an equation for the angular momentum between points A and P, A being the apogee and P being the perigee. Angular momentum is conserved because the only force that we see acting on the rotating body is your F of g pointing towards the sun. And no matter where you are, this will point towards the sun, directly parallel to your orbital radius. If F is parallel to your R, then torque will equal 0. There's no perpendicular force acting on the equation, therefore torque is 0. Therefore, there's no change in angular momentum. Next, or the next part of part A, is going to be the net angular momentum at A set equal to the net angular momentum at point P. We can find this with the point mass angular momentum equation, which we know is mv, in this case mva, times ra equals 2 mvp rp. M's cancel out because the mass of the orbital body will not change. VARA is equal to VP RP. Next, you have explained why mechanical energy is conserved, then give an equation for the mechanical energy between the 2 points. We know mechanical energy is conserved because the farther away you are from your orbit, the slower you're going to be moving. To maintain proportion in this, the farther away you are from your orbit, the smaller your velocity is, but the smaller the gravitational potential energy, or the greater the gravitational potential energy is going to be. It's going to be less negative, so there's less to detract from it. Same here. You're moving faster because your radius is smaller, but because your radius is smaller, there's going to be an even smaller gravitational potential energy, which will balance out the system because it's negative. There's going to be more subtracted from the larger quantity and less subtracted from the smaller quantity. You can find this through K at A plus UA is equal to KP UP plus UP. Substituting in equations, we know 1/2 MVA squared plus negative G MS M over RA is going to be equal to 1/2 mvp squared plus negative g ms m over rp. The mass of the orbiting body cancels out because it's a constant across all 4 terms. VA squared over 2 minus GMS for RA is going to be equal to VP squared over 2 minus GMS for RP. That is the equation to be found from the conservation of energy between points A and P. part C will utilize both of these equations. Part C is asking us to prove that V of P is equal to 2 GMS over RAVA minus VA. We can find this by starting with the VA squared over 2 minus GMS over RA is equal to P squared over 2 minus GMS over RP. Using also the equation found in part 1, VARA is equal to VPRP. You can isolate for R of P by dividing both sides by VP to get VARA over VP equals RP. Plugging this into our equation and simplifying all of the terms, let's first write that out. GMS over VARA over VP. These terms are the same thing. And then we can simplify everything, all of these fractions, by moving VP to the top and multiplying every term by 2 to get VA squared minus 2 GMS over RA is equal to VP squared minus 2 GMS R or VP over RA VA. We can switch these two variables around, add this to this side, subtract this from this side to get VA squared minus VP squared is going to be equal to 2 GMS over RA minus 2 GMS VP over RAVA. Let's do two things right now. Recognize this is a separation of variables to get VA minus VP times VA plus VP, and multiply this term by VA over VA, which equals 1, but it gives us this solid term that we can pull out of the equation, 2 GMS over RAVA. It's going to be equal to VA minus VP. You have VA minus VP on both sides, so you can cancel it out. VA plus VP is equal to 2 GMS over RAVA. Subtract VA from both sides, you get VP is equal to 2 GMS over RAVA minus VA, which is